We're heading to Betelgeuse, a massive red supergiant star roughly 650 light-years away in the constellation Orion. As one of the brightest stars visible from Earth, it marks the hunter's right shoulder and has captivated astronomers for centuries with its fiery red hue and unpredictable behavior. This star, also known by its Bayer designation Alpha Orionis, stands out in the winter sky, rivaling even Sirius in apparent brightness at times. Its name, derived from Arabic, roughly translates to the giant's shoulder, fitting for a celestial behemoth that has inspired myths and scientific inquiry alike. Leaving Earth's atmosphere behind, we soar into the void of space, passing the familiar planets of our solar system: Mercury's scorched surface, Venus's thick clouds, Earth's blue marble, Mars's rusty dunes, and the gas giants beyond. As we accelerate outward, the sun shrinks to a distant point of light, and we enter the true interstellar expanse, where the pull of gravity from our home star fades into insignificance. To make this journey feasible in our imagination, we're accelerating to an incredible speed of 1 light-year per second. At this pace, we'd zip past the nearest star, Proxima Centauri, in just over 4 seconds, and traverse the distance to the Orion Nebula, a stellar nursery about 1,344 light-years away, in under 23 minutes. Imagine that. What takes light over a millennium to travel, we cover in less time than a short commute. In contrast, humanity's fastest spacecraft, like the Parker Solar Probe, hurtles through space at about 430,000 miles per hour, or roughly 0.064% the speed of light. It would take millions of years to cover even a fraction of this path, underscoring the mind-boggling distances involved. Our hypothetical velocity defies physics as we know it, ignoring relativistic effects like time dilation, but it allows us to bridge the cosmic gulf in moments. As we gain speed, the stars begin to streak by like fireflies in a cosmic wind, blending into luminous trails that highlight the density of our galactic neighborhood. As we navigate through the Milky Way, we encounter the dense arms of our spiral galaxy, filled with billions of stars, gas clouds, and dust lanes that obscure distant views. Betelgeuse resides in the Orion Arm, a bustling region of star formation where gravity weaves massive structures like molecular clouds and open clusters, such as the famous trapezium cluster at the heart of the Orion Nebula. These arms are not static. They rotate around the galactic center, a supermassive black hole called Sagittarius A star, which holds the galaxy together with its immense gravitational influence. Beyond our immediate path, the galaxy's core looms in the distance, a swirling hub of activity bound by dark matter, an invisible scaffold that makes up about 85% of the universe's mass, and dotted with ancient globular clusters orbiting like satellites. Interspersed are regions of hot ionized gas, glowing nebulae where new stars are born from collapsing clouds, and remnants of old supernovae that have enriched the interstellar medium with heavy elements like iron and gold, the building blocks of planets and life.
Along the way, we pass notable neighbors like Rigel, Betelgeuse's blue supergiant counterpart in Orion, shining with intense ultraviolet light that ionizes surrounding gas and creates glowing H2 regions. Rigel, about 860 light-years distant, is a stark contrast to Betelgeuse, hotter, bluer, and part of a multiple star system. Recent observations, including those from the James Webb Space Telescope, launched in 2021, have revealed dynamic star-forming regions here, where protostars accrete material from protoplanetary disks, potentially birthing new worlds. Questions arise. Could rogue planets or hidden exomoons exist in these interstellar gaps, drifting alone in the cosmic dark, ejected from their parent systems by gravitational perturbations? Or perhaps brown dwarfs, failed stars, that glow faintly in infrared, lurk undetected. The journey also takes us near the Horsehead Nebula, a dark molecular cloud silhouetted against bright emission nebulae, a testament to the ongoing cosmic drama, where birth and death interplay across eons. The farther we travel, the more we grasp the immense scale of even our local cosmic neighborhood. If the sun were a grain of sand, Betelgeuse would be a colossal boulder, dwarfing everything in its vicinity, while the entire solar system would fit comfortably within its bloated atmosphere. This journey reminds us how our solar system is just a speck within the vast tapestry of the Milky Way, itself one of trillions of galaxies in the observable universe, which spans about 93 billion light-years across. Zooming out further, the Milky Way is part of the Local Group, a collection of over 50 galaxies, including Andromeda, which is on a collision course with us in about 4.5 billion years, leading to a galactic merger that will reshape both. Beyond that lies the Virgo supercluster, and even larger structures like the Laniakea supercluster, encompassing hundreds of thousands of galaxies bound by gravity's web. These hierarchies reveal the universe's fractal-like organization, where patterns repeat on ever grander scales, challenging our human-centric view and evoking a sense of profound humility amid the infinite. Betelgeuse is a variable star in the late stages of its life, with a mass around 18 times that of the Sun, and a surface temperature of about 3600 Kelvin, giving it a cool reddish glow compared to our Sun's 5500 Kelvin yellow-white radiance. It's only about 10 million years old, remarkably young for a star, as our Sun is 4.6 billion years old. But its immense size means it burns fuel rapidly, fusing heavier elements in its core like helium into carbon and oxygen. This leads to dramatic brightness fluctuations caused by enormous convection cells, where hot plasma rises and cools, and periodic ejections of dust clouds that temporarily dim the star, as seen in the Great Dimming event of 2019-2020, when it faded to about 35% of its usual brightness. Astronomers classify it as a semi-regular variable, with pulsation periods ranging from 185 to 2100 days, influenced by its unstable outer layers. Recent studies using instruments like the Atacama Large Millimeter Sub-Millimeter Array have mapped its asymmetric shape and mass loss, shedding material at a rate that creates a circumstellar envelope extending far into space.
Finally arriving at Betelgeuse, we're awestruck by its sheer enormity, a radius nearly 700 times that of the Sun, large enough to engulf the orbits of Mercury, Venus, Earth, and Mars if placed at our system's center, stretching out to about 1,000 astronomical units. Its mottled surface bubbles with giant plasma convection zones, like boiling soup on a stellar scale, each cell larger than our entire solar system, causing the star to appear lumpy and irregular in high-resolution images from telescopes like the Very Large Telescope, or VLT, in Chile. The atmosphere is tenuous and extended, with winds driving material outward at speeds up to 17 kilometers per second, forming bow shocks as it plows through the interstellar medium at 30 kilometers per second relative to nearby stars. Recent 2025 discoveries reveal a companion star orbiting every few thousand days, nicknamed Beetle Buddy, a smaller, hotter star that may interact with Betelgeuse's envelope, triggering outbursts and influencing its pulsations, though debates continue about whether it's a true binary or a line-of-sight coincidence. When Betelgeuse eventually explodes as a supernova, possibly within the next 100,000 years, though predictions vary, it will outshine the full moon from Earth, visible even in daylight and casting shadows at night for weeks, briefly becoming the brightest object in the sky after the Sun. This cataclysmic event, a Type II supernova, will eject its outer layers at thousands of kilometers per second, forging elements heavier than iron in the blast and dispersing them across the galaxy to seed future star systems. The remnant could be a neutron star or black hole, depending on the core's final mass, and the shockwave might trigger new star formation in nearby clouds. From Earth's perspective, the explosion poses no direct threat due to the distance. Radiation would be diluted, but it would provide an unprecedented astronomical spectacle, allowing real-time study of stellar death. This leaves us to wonder about the cycles of creation and destruction in the universe, where the end of one star births the ingredients for new worlds, perhaps even life-bearing planets like our own, perpetuating the grand cosmic narrative across billions of years.